Testing the closed caption. This is clearly the better of the two mics. Actually, maybe not. All right, let's see. Testing this mic to see which one picks up everything better. Okay, looks like this one's better. And it's on. Everything that we're saying right now is on Zoom and on the live stream.
Right, so I'll turn it back off.
On the hosting. No. Wait for
So much to set up for this every day. You really got it down to a science though, or an art. I don't know.
Now I just need to connect this down here and then we'll be good to go.
Okay.
Everybody. No?
It's a little blue, but I thought that just meant standby. It was
No.
bluer before I tried to turn it off. Yeah.
It's picking up everything we're saying.
Shruti, do you hear me?
Yes.
Okay, but I don't hear you. So we're just working on the, yeah, there we are, audio projection locally.
Okay.
That one, it's outside. Yeah, it's not that. It's not. Everybody else is going to see that.
Okay, we'll be back to you in just a moment.
Literally something we should have super practiced that. Yeah. Oh, I see. The audio will go. Yeah, the computer is staying there.
Okay, so this, now this doesn't go through. Shruti, if you still hear me, can you say something? Let's see if it gets to the room.
I can hear you. Hello?
Actually, when you talk, it might come through too.
Testing, testing.
Hello? I can hear you.
We're just handling something right now. So we're just trying to get the speakers through. See if we can test it.
Test, test, test.
I can hear you.
Is that not?
Yeah,
good enough?
we're okay, Shruti. We're just
Well,
trying to
she
figure.
hears me, so
Yeah,
it's-
she can hear us fine. But it's not coming over them. Usually that means I need to plug the plate in. So I have an idea.
Number nine, number nine.
Ask her to say something.
Shruti, can you say something?
Hello? Can you hear me?
Try that again.
Can you hear me? Hello?
Yes, but.
I'm worried
We're just
that,
not getting you through the room speakers yet.
yeah, I'm just worried if if there's a problem at my end or your end.
The issue isn't you. I'm just trying to sort out the speaker system right now. Sorry.
No, no, it's fine.
Don't worry, if we
I
delay a
promise we're
little bit,
getting
it's not
closer.
the end of the world. You can just delay your talk just a bit while we do it.
That's fine.
Yes, I know everybody on Zoom can hear, but the room can't hear that. So thank you.
But this is the room either. Is it the Zoom audio settings that maybe aren't on the right speaker? This,
Well, that's there's two speakers. That are coming through. The problem is that there's two speaker devices. Zoom didn't do it. Zoom didn't do it.
Like with the speaker of that TV.
Well, I don't know if it's the room PC that's trying to do it now or my PC that's trying to turn it on.
You just have all the good luck, Shruti.
It's not our, she can hear on, I can't hear. I can hear her on this computer. Yeah. So she's in, but I can't hear her. Don't think so. Usually if I plug this into here, then my audio would be. But it's not. Lillian. Whatever comes through my microphone should come through here. I think it's something that's disconnected on the way. I can hear that, but you guys can't hear it. That's interesting. Yeah, we don't hear the speaker. That's the problem. About the audio.
Number nine. Shruti, can you say something?
Hello? Can you hear me?
Brilliant. We hear you. All right. Sorry about the delay. Let me just lower the volume a little.
No problem.
Played. Is that good enough?
As long as we can hear him.
Test one more time. I turned the volume down a bit.
Can you hear me? Is it good?
Yeah, I think that's good.
Okay, we'll just go with that.
All right. I think we're just going to go with that. In that case, thank you very much. Sorry, everyone, for the delay and the reverb. I'm very pleased to be able to introduce to you Shruti Puri, professor at Yale University. I'm sorry that she can't be with us in person, but we're going to fix that at some point in the future.
Okay, now I can hear it.
So Professor Puri did her first degree at the IIT. She then did her PhD with Yoshi Yamamoto at Stanford. and went on to do a postdoc with Alexandre Blais at Sherbrooke, who many of you know, and another postdoc with Steve Gervin at Yale, who many of you also know, and has really been one of the pioneers in a lot of exciting work in quantum information that we're going to be hearing about today. She's won many awards and accolades in her career already. And I'll just mention the most recent one, very exciting. She was just awarded the APS Landauer Bennett Prize in quantum information. So some very exciting names attached to her work. So with that, I'll just pass it over to you, Shruti. Thank you very much for being here.
Thank you so much for the introduction. I hope you all can hear me, and please stop me if something goes wrong. I also have my email open here, so if suddenly somebody loses internet connection, if you can email me, I'll see that. I'm so sorry that I couldn't make it. This is the second trip I've missed due to visa issues this year. Hopefully things get better as years progress, but we'll see. All right. So today I want to talk about how do you characterize good qubits and what makes a good error correcting code. But before that, I would like to acknowledge all my collaborators, in particular, Jeff Thompson from Princeton, who is the experimentalist working on neutral atom qubits. And a lot of our recent work has been in collaboration with him. And I would also like to acknowledge all the students and postdocs who actually make the work happen. All right. So suppose I give you two types of qubits, A and B, and I give you, some sort of average information about average error rate, or if I give you information about the fidelity of qubits A and B, and if, say, the fidelity of the qubit A is better than the fidelity of qubit B, then which one is better in terms of error correction? So for a long time, fidelity has been a metric for defining or characterizing qubits in our field. And with that characterization, you would see that if the fidelity of the qubit A is better than B, then that is a better qubit to use. However, what is important is not the fidelity. What is not important is just the fidelity, but what is also important is the structure of noise, or the detailed properties of noise. So different kinds of noise can ultimately lead to the same average fidelity, but they can perform very differently when considering an error correcting code. So let's take the example for a error that we call erasure error. This is like saying that your qubit state 0 or 1 left the qubit subspace and went to some other state, some excited state or some leaked state E, and you as a user have a flag that you know that this error has actually happened. So this is called as erasure error. So there's erasure error because you have the flag. You at least know which qubit had an error, so you know which qubit you need to fix in your system. So this is an easy type of error to correct. You can also have an error, which is called biased erasures. Here, the erasure happens only when the qubit is in 1. So again, this is like an additional information that you get. And it turns out that in an error correcting code, biased erasures are easier to correct than standard erasure errors. You can also have what I call as poly errors, and these are the standard kind of errors that people think about, which is like the action of a poly X or poly Y or poly Z operator to your qubit state. So if you have a single qubit, it's in some arbitrary superposition state, then your state 0 can go to 1. That's like the action of the poly X operator. You can get a phase between the 0 state and the 1 state, and that's the poly Z operator. And if you get both a bit flip and a phase flip at the same time, then that's like a poly Y error onto your state. So poly errors are harder to correct than erasure errors. So they are less desirable than erasure errors. Even for poly errors, you can have what we call as biased Pauli errors. Here, the probability that you have an probability of getting one type of error, so say probability of a Z error, is much higher than the probability of an X or Y error. So here, you can also define what we call as a bias, which is the ratio of the Z errors to the X and Y errors. So it's the ratio of the dominant errors to the non-dominant errors. And it turns out that biased Pauli errors are easier to correct than general Pauli errors, where the probability of X, Y, and Z are the same. The most difficult type of error to correct is the leakage error. Leakage error is kind of like erasure, but you don't have the flag. So your qubit left from the 1 or 0 state, it went to some other state, and you don't even know that this has actually happened. So this is the hardest type of error that you want to protect your system from. So let's let me go a little bit deeper, more concretely into this noise hierarchy that we saw. So let's look at the Pauli noise. So again, this is a Pauli channel with probability X, Y, and Z. You apply X, Y, or Z error to your quantum state. The total error rate is the probability of X error plus probability of Y error plus probability of Z errors. The question that you should ask is, what is the capacity for a qubit experiencing the Pauli noise channel to communicate quantum information? So this is what is called as the quantum channel capacity. Which is like, at what rate can you pass information through this noisy channel reliably? It's very, very hard to calculate quantum capacities, but you can kind of find a lower bound for the capacity for the Pauli noise channel, and that's what I have written over here in this formula. So if the achievable capacity is given by this formula over here, this is 1 minus some quantity, which is basically the Shannon entropy. So what it is saying is that if the entropy of your noise channel, not the total error rate, not Px plus Py plus Pz, but if the entropy of the noise channel, which is related to this quantity over here, if that is small, then you can pass more quantum information through this noisy channel. So ultimately, what you want to do is not necessarily minimize the total error rate, which is Px plus Py plus Pz, but you want to minimize the entropy of noise. So what is important is the entropy of noise and not the total error rate or the fidelity or infidelity by itself. So suppose I have, I can allow for a biased noise channel. So I have this quantity bias, which is defined as the ratio of the dominant error, which I'm assuming to be Z errors, divided by the non-dominant errors, which is the X and Y errors. So what I can calculate this quantity over here for such a biased noise channel, and whenever this quantity becomes equal to 1, that means that the achievable capacity becomes 0. That's what we call the threshold. So if this quantity, if Px, Py, Pz are too large, then this quantity is going to be large and the achievable capacity is going to be negative. So that's bad. As you slowly start decreasing these probabilities, this capacity will suddenly become positive. And the place where it becomes 0 is basically called the quantum capacity threshold. It's the smallest error rate that any error correcting code will be able to tolerate. So I can plot the plot this threshold, the value of the total error rate, so the value of Px plus Py plus Pz, at which the quantum capacity vanishes as a function of the bias. So if the bias is small, that is, if the probability of X, Y, and Z errors is the same, then this threshold is about 20%. But if my bias is large, that means the X and Y errors are really small compared to the Z errors, then the threshold increases. So what this is telling you is that the ability for us to transmit information through a noisy channel increases as the bias increases. So it's not just the total error rate that matters, it is the entropy that decides what is the tolerance to this kind of noise in the system, and that tolerance increases as the bias increases. Now let's look at the erasure channel. Erasure is one of the few channels for which we actually know exactly what the quantum capacity is going to be, and similarly for biased erasures. So the capacity, the quantum capacity for the erasure channel is 1 minus 2p, where PE is the probability to get an erasure. And that for the erasure channel, the biased erasure channel is 1 minus PE. So whenever 2PE is equal to 1, or when that means that PE is equal to half, then I'm at the threshold for the erasure channel, whereas when PE is equal to 1, I'm at the threshold for the biased erasure channel. So again, what this is saying is that I can tolerate the quantum for the same amount of PE, the capacity to transmit information through a biased erasure channel is higher than through a erasure channel. And by the way, these quantities 2PE and PE is also related to entropy, defined in a certain way. So the threshold for the biased erasure, for the erasure channel is 50% or half, and the threshold for the erasure channel is 1. Now you can also define a noise channel where you can have some amount of erasures and some amount of poly errors. So we can define a erasure fraction, which is the probability of erasure error divided by the total probability of error. So the total probability of error is probability of erasures plus the probability of poly errors. And I can, again, look at, I cannot exactly calculate the capacity for such a noise channel, but I can bound it, and I can get a lower bound on the thresholds for the total error rate and plot it as a function of RE. And as you can see, as the when RE is 0, that means when all the errors are poly errors, then the tolerance, the threshold, or the tolerance to the noise is about 20%. That means all the noises of the erasure type, the threshold is about 50%. This is for an erasure channel, and the threshold increases if you go from erasures to biased erasures. Again, what this is saying is that the tolerance to the noise is given by not just the total error rate, but the entropy of noise. And so that is the number that we should be thinking about, not just the fidelity. Another nice thing is that if I have a quantum error correcting code that can correct for some number of poly errors, then it can actually correct for twice as many erasure errors. So basically, you get more bang for your buck. It takes a lot of overhead to build an error correcting code. So the same overhead error correcting code will give you a better protection if you have erasure errors compared to if you have poly errors. Now, let me try to explain. I'll give a very simple example to demonstrate why biased erasures are going to be better to correct versus just, say, poly errors. So let's take the example that I only have Z errors in my system. And in order to correct for Z errors, I can just implement a simple, what we call a quantum repetition code. Let's implement a simple 3-qubit quantum repetition code. So that means that any a single bit of logical quantum information is stored in the state of 3 qubits, as shown over here. And in order to detect errors, I measure the correlations between the two pairs of qubits, and these correlations are the measurements of poly X operators on qubit 1 and 2 and poly X operators of qubit 2 and 3. Okay, so suppose there was a Z error on the first qubit. So Z error on the first qubit takes the plus state to the minus state and the minus state to the plus state. So now if I measure the x1, x2 operator, then I will see x1, x2, the measurement outcome I will get is -1, and the measurement outcome of x2, x3 will be +1. It's very simple to work out. These states I've written down are actually the eigenstates of these x1, x2, and x2, x3 operators. So it's a very easy math problem to work this out. Now, there's another way, there's another possibility which could have given you the same measurement outcome. So you could have, instead of having an error on the first qubit, you could have had an error, 2 Z errors, one on the second qubit and one on the third qubit, in which case this is the state that I get. And again, if I measure the poly operators, I get x1, x2 as -1 and x2, x3 as +1. So now if I make a measurement of my poly operators and I get -1 and +1 measurement outcomes, I have to decide whether a Z error happened on the first qubit or Z errors happened on the last 2 qubits. So how do I make a decision on which one I think has happened? If errors happen independently, and if the probability of a single Z error is PZ, then the probability of 2 Z errors is going to be PZ square. So it's more likely than a single Z error has happened rather than 2 Z errors happening. So whenever I see the -1 +1 measurement outcome, I should assume that a single Z has happened on the first qubit. The probability that I have failed, the probability that I have made a wrong guess, is the probability of having 2 errors, and that goes as PZ square. So I've actually now suppressed my failure rate quadratically from PZ to PZ square. So I've succeeded in doing error correction. So in general, you can build an n-qubit repetition code. So this was a 3-qubit repetition code, which corrects for 1 Z errors. In general, you can make an n-qubit repetition code, which corrects for n + 1 over 2 errors. And you can show that if, again, errors are happening independently, then the probability of a failure is going to decrease exponentially with n. This is as long as p is smaller than 0.5. So the threshold is for just pure poly Z errors is 50%. Okay. Now let's take the example of a biased erasure. So that means my one state can go to the E state, but the 0 state doesn't go to the E state. And I also assume that the flags that I get also tell me exactly which qubit was erased. So if I get a red flag, then the first qubit had an erasure. If I get a blue flag, it was the second qubit. And if I get a green flag, I get the third qubit that was erased. So, okay, suppose I get the red flag. That means the one state went to the E state. So then this is the state I am left with. And now you see the first qubit has become unentangled with the rest of the system. Now what I'm going to do is I'm going to replace this E state with the one state. I'm going to bring in a fresh qubit prepared in the one state and replace the E state with the one state. And now I'm going, so if you look at this starting state and the state I have on the right-hand side over here, it's like I have acted a identity plus a Z on this state. So if on the first state, I apply identity plus Z, I get this last state over here. So this is almost like a poly error, but it is a poly error in almost a known location, like because I know that only, I get a red flag, so I know that something has happened to my first qubit. Okay, so we're not done yet. How do I actually fix the error? How do I go from the state on the right to the state on the left? Again, measure my stabilizers, and now I have two possibilities. If I measure, if I measure the operators x1, x2, and x2, x3, I will either get a +1 measurement outcome, or I will get a -1 measurement outcome. If I get a +1 measurement outcome, I know that I've projected myself onto this state. And if I get a -1 measurement outcome, I know I've projected myself on this state. So if I get a -1 measurement outcome, it's like, there was a Z1 acting on the first qubit, and I can, again, go and correct for a Z on the first qubit here. So I can recover my initial state. But you see that the difference here was that the difference between here and the previous polynoise case was that I know exactly that I need to apply a Z to the first qubit. There was no confusion between Z1 and Z2, Z3, because I knew that I got the red flag and only the first qubit could have had an error. So you see, I'm going to do better now. So the only way I will not be able to correct for any errors is if all the 3 qubits get erased. So it turns out in this case, the probability of illogical error goes as p cubed. So you see, you're doing, so in case of a 3 qubit repetition code with the poly noise, the error rate went as p squared, but with the biased erasure noise, the error rate went as p cubed. In general, for an n qubit repetition code, the logical failure rate will be if all the n qubits had an erasure error, and that would be p to the n, and the threshold is 1, right? Basically, as long as p is smaller than 1, this number, the logical failure rate, can be made exponentially small by increasing the number of the size of your code or the number of qubits in your code. So this kind of captures, this simple example captures the difference between the power of erasure errors compared to poly errors. Erasure errors are much easier to correct than poly errors, just because I have the location of the error known to me. In general, you can, like I said, you don't necessarily have to have biased erasures. You can have general erasures. So in this case, when I get a flag, I don't know if 1 has gone to E or if 0 has gone to E. So this is unbiased erasure because you can go to the E state from either 1 state or 0 state. So if this error had happened, my state after the error would be the state on the right here. Otherwise, it would be the state on the bottom right over here. So now you see there's a little bit more complication introduced here, because now I've introduced an additional phase error because I did not know if 1 went to E or if 0 went to E. So I don't know whether, I have the state on the top here or I have the state on the bottom here. So there's a little bit more challenge in this case. And therefore, it's a little bit harder to correct for unbiased erasures than biased erasures. I don't have an intuitive argument at the moment to tell you why the threshold for this should be 50%, but you can just from the no cloning quantum no cloning theorem that you must read in your undergraduate course even nowadays, even from the quantum no cloning theorem, you can derive that the threshold for this type of error should be 50%. And you can also show that if you use something like what we call a surface code, it's a more complicated code than the repetition code, the logical failure rate decreases exponentially with the size of the code. Okay, so clearly we see that erasure errors are really, really nice. So we would like to design qubits where my noise channel is erasures rather than poly. I would like to suppress the poly errors, but it's okay if I get a little bit of erasure errors into the system, because I know subsequently it's going to be easier for me to correct it. Now, what are the requirements for having a qubit with an good erasure channel? Basically, how do you get this flag? So, your qubit went from 1 to the E state. Now you somehow want to run an experiment that gives you this flag and tells you that, hey, I've gone to the E state. So usually we perform some sort of detection, we perform some sort of measurement to see whether my qubit left the computational subspace and went to the E state. Importantly, that erasure detection must be QND on the qubit subspace. That means that if the qubit remained in the computational subspace, I should not add errors into it. Only if the qubit went to the E state should I know something about the qubit. Otherwise, I should not gain any information about the qubit. So the flag, the erasure detection must be QND. You should also have good spatial resolution. That means that you need to know exactly, which qubit got erased. Like if you are not sure whether, my erasure was on the first qubit or the second qubit, then that reduces my ability, or that is detrimental to my ability to correct for noise. So I need my erasure detection pulse should have a good spatial resolution. You can also get false positives, which means that, sometimes the qubit didn't get erased, but you declare that it was actually erased. This is still a little bit more tolerable. This in effect introduces new erasures into your system, and as long as the rate is small, you're fine. The more problematic thing is false negatives. That is, erasure happened, but you did not know that it happened, and that's basically a leakage error. And that's, like I said, very, very hard to correct. And the most common way we think about correcting for leakage error is something called as measurement-based or teleportation-based error correction. It's just a little bit more annoying to correct for leakage than general poly errors or erasure errors. Okay, so hopefully I've convinced you that whenever you're doing your experiment, whenever you're building your qubit, don't quote one number, which is the fidelity. Please also look at what is the detailed noise channel of your qubit. That's very important. You can have a qubit with poly noise channels, say the error rate is 1%, but you can have an qubit with an erasure noise channel with an error rate of 1%. In terms of error correction, the 1% erasure channel is much, much, much more preferable than the 1% poly channel. The capacity of the erasure channel is higher than the capacity of the poly channel. Okay, so, oh, I'm sorry, somehow this reference is appearing in the middle here. Apologize for that. So we, in a work with Jeff Thompson, we designed a neutral atom qubit where the dominant errors were erasure errors. So you have your ytterbium atom qubit. It has many energy levels. You choose usually people pick the ground state of the atom to encode a qubit, but the idea here is that we're going to choose a metastable states to encode the qubit. So we choose some metastable states, which I'm just labeling for convenience as state 0 and 1 to encode the qubit. Now, if I have two qubits, two of these neutral atoms next to each other, and they're in their computational subspace, they don't really talk to each other. So in order to do gate operations, in order to entangle the qubits, we have to excite the qubits onto the Rydberg state. So we apply a pulse to excite the one state to the Rydberg state, and through Rydberg blockade, the gates actually happen. The main source of errors here is that during this gate operation, the Rydberg state decays to the ground state. So the Rydberg state can actually decay back to the computational subspace, but that's very, very rare. The more dominant thing that happens is the Rydberg state going to the ground state. So what we can do is that we can now apply an additional pulse to check whether my population went to the ground state or not by some fluorescence transition. Importantly, this extra pulse, this blue pulse that I've shown here, the extra pulse that you apply does not perturb the qubit. It only checks the population in the ground state. So it is a way to do QND erasure detection. Okay, so let me kind of summarize what I just said. Suppose you had your two atoms, you did your control Z gate on your system. So these when you bring the atoms close together and you excite the one state to the Rydberg state, the gates that happen is a 2-qubit control Z gate. After the gate, you're going to apply. Some error could have happened. Your Rydberg state might have gone to the ground state, for example. You're going to apply your erasure detection pulse, and the erasure detection pulse will say, yes, I went to the ground state. Now you remember that only the one state actually coupled to the Rydberg state. The 0 state doesn't couple to the Rydberg state. So again, this is like biased erasures, because if you see fluorescence from the ground state, that means that atom must have started in the one state. So this is again like biased erasures. And so if you see an erasure, if your erasure detection pulse says, hey, I'm erased, you will put a fresh atom back in the one state and continue doing your operation. And like we saw in the previous case, this effectively just introduces at most a Z error into your system. So in fact, we can show that the error channel for this 2-qubit gate in the neutral atom system is effectively given by random application of identity or a Z on one of the 2 qubits. Of course, there's a chance that even if there was no erasure, there's some chance that you get poly errors because of transitions between the 0 and 1 states themselves, but this is very, very weak. The lifetime of the metastable state is still very long, like 20 milliseconds or even more. And so the probability that you get a poly error is still very small. So this is like a erasure biased qubit where the probability 98, we expect in this particular setup that about 98% of total errors are going to be erasure errors. So the erasure fraction, the expected erasure fraction in this system is about 98%. In Jeff Thompson's group, they actually recently demonstrated this architecture. They demonstrated a Rydberg atom with erasure, Rydberg atom gates with erasure conversion. In the first experiment, the erasure conversion wasn't 98%. We know exactly what the issues are, and hopefully in the second experiment, this number should go much higher. In the first experiment, the erasure fraction was only 50%. But again, first experiment and a lot more work is going on. Since I work on erasure conversion, a lot of other platforms, a lot of other qubit architectures and platforms have tried to design their own qubits such that most of the errors are erasure errors and poly errors are suppressed. In Yale in particular, we are considering what we call dual rail qubits. These are super qubits encoded in the presence of a photon in one of 2 microwave cavities. So here the big circles are microwave cavities. And if there's a photon in the first cavity, but not in the second cavity, we say it's qubit state 0. If there's a photon in the second cavity, we say it's qubit state 1. And so the dominant error is due to photon loss. And in this case, if there's a photon loss, the 1, 0 or the 0, 1 state goes to the 0, 0 state. And so if you're able to check whether your cavities went to the 0, 0 state or not, then you are able to do erasure conversion. The way we do that is actually using a transmon. In particular, we use a transmon in which we are able to control 3 levels, G, E, and F. And I'm not going to go through the details. You can, if you're interested, you can look at the papers. But the information about whether an erasure has happened or not is encoded in whether the transmon ended up in the G state or not in the G state. So we do some sort of interaction between the cavities and the transmon to map the information about erasures from the cavity onto the G or not G state of the transmon. There's also work on dual rail transmon qubits in Amazon, and they also have some fantastic experiments. There's also work in trapped ions looking at designing trapped ion qubits with dominant noise as erasure channel. Okay, so I just said that the erasure errors are good errors. We can correct them. Some errors are good errors, some errors are bad errors. But you also need a code. You need a good code which is able to effectively correct for the error that is dominant in your system. Not all codes are going to be good to correct for the specific error that you're looking at. So if you look at, for example, just a regular, the most famous example of an error correcting code is called the CSS or the surface code. You know, if you're following work from Google, IBM, and all these big companies, they all are trying to build a surface code. So what is the surface code? You have qubits arranged on a 2D lattice, and the operators, which we call stabilizers, that you use to detect errors are 4-body operators acting on 4 qubits around each of the plaquettes. So you have 2 types of operators. One operator is the 4-body X operator acting on the 4 qubits around the gray plaquettes. And you can have the 4-body Z operator, which acts on the 4 qubits around each of these white plaquettes. You can also have what we call the XZZX surface code, which is very similar to the surface code on the left, the conventional surface code, except that you only have one type of operator that you need to measure, and that's the 4-body XZZX operator acting on the 4 qubits around each of the plaquettes. Now, the number of errors you can correct depends on the dimensionality of these codes. So the number of poly Z errors you can correct depends on the length of this lattice, and the number of X errors you can correct depends on the height of this lattice. The number of Y errors you can correct is, so if a code can correct for X or Z errors, it can also correct for Y errors. So usually we only talk about correcting for X and Z errors. Okay, now what happens in the regular surface code if you have just a Z error? Suppose you only have a Z error on the qubit that I've marked over here, then the measurement outcomes of the operators on the top and the bottom on the gray plaquettes will be minus. So if you see those 2 operator measurements to be -1s, then you know that there was a Z error on that specific qubit. If there was a Z error on this qubit, it will cause -1 outcomes of the plaquettes to the left and to the right. In contrast, if you look at the code on the right, a Z error will only anti-commute, will only produce a minus sign on the operators to its left and the right, but it will never produce -1 signs on operators at the top or the bottom. So if I put a Z error over here, it also produces -1 sign here and here. If I put a Z error here, it also produces a -1 here and here. It will never, a Z error anywhere will never produce minus signs vertically. It will only create minus signs horizontally. This is, which is very different from the code on the left, in which a Z error can produce both vertical and horizontal minus signs. So it turns out that this is related to some symmetry properties of the code. So we say that the XZZX code has one-dimensional symmetries to Z errors, which are absent in the surface code, and having one-dimensional symmetries actually makes error correction easier. So the XZX code is going to be more effective against correcting Z errors than the regular surface code. In fact, for the XZX code, it actually reduces to a repetition code for Z errors. So in the first few slides when we were looking at the repetition code, the XZX code behaves exactly like the repetition code if I just have Z errors, and that's due to the symmetry properties that I just pointed out. So now you can look at the threshold as if threshold for error correction for these codes as a function of noise bias. And for the XZX code, the threshold increases and as a function of bias, but for the code on the left, for the regular CSS surface code, the threshold actually decreases if you increase the bias. Again, this is because of the symmetry properties. The solid line over here is actually the threshold line predicted from the hashing bound, the quantum capacity bound that I showed in the first slide. Remarkably, the XZX code follows the threshold for the XZX code follows this optimal, well, not optimal, the lower bound to the quantum capacity for a while, but then it actually does better than this lower bound. And this is important for experts in the audience because it's actually very hard to find codes that do better than this lower bound on the quantum capacity threshold. So XZX code remarkably is able to actually do that. Okay, but nonetheless, the point being is that depending on your noise, you also need to design a good code for that specific noise. Not all codes are created equal. In fact, you don't just have to think about the codes in terms of the thresholds, but you can also think about the codes in terms of the overhead that you need. So if you have only Z errors in your system and you're implementing the XZX code, then you can actually use a thin XZX code where DX is much smaller than DZ. In fact, if there's no X errors or Y errors, then you can just use a single line rather than this two-dimensional lattice. You can just use a single line of qubits, and that basically reduces to the repetition code. Of course, in no system, X or Y errors will be exactly 0. But even if you have, some small amount of X or Y errors, that means if you have a large bias, you can just decrease, you can change the aspect ratio of this. You can decrease the X, you can decrease the height of the code, and you can increase the length to correct for more Z errors rather than X errors. And this helps you save on overhead. You could not do this in the, it's non-trivial to do this in the CSS surface code. Okay, it's not only important, not only is the code important, it's also important to look at how you actually implement the code. That is, how you actually measure these operators. So if you look at this circuit over here, the way we measure the XZX operators is we put an auxiliary qubit at the center and do a bunch of control NOT and control phase gates with the neighboring qubits, and then measure the this auxiliary qubit, and the measurement outcome of the auxiliary qubit effectively tells you about the XZX measurement outcome. So the way you would do this measurement, sorry, there was something on the chat. I just want to make sure I'm not, okay, yeah. Right, so if there is a, so when you were, suppose you're doing a control NOT gate, so you have your auxiliary qubit and you have your data qubit on which you're trying to do the control NOT gate, then it turns out that if you have Z errors in your system, then a Z error can, during the gate, can actually propagate to a combination of Z errors and Y errors in the system. That means that even though physically your qubits only have Z errors, the act of doing this operation is going to convert Z errors to Y errors. That means your system is no longer biased noise anymore. That's bad. In fact, it was first conjectured in this paper by Alifers and Preskill in 2008 that it's impossible to do a C0 gate that preserves the noise bias in a strictly two-level system. We were able to later show that if you have continuous variable qubits, then you can actually, they're not exactly two-level systems, they're not strictly two-level systems, they're continuous variable systems, and then that allows you to go around this no-go theorem predicted by Alifers and Preskill, and that allows us to do actually a bias-preserving C0 gate. So if you have a bias-preserving C0 gate, then only you can, well, if you have a bias-preserving C0 gate, then it's very easy for you to realize the XZX surface code and take advantage of bias noise. And we actually also have a paper examining the XZX surface code for these continuous variable bosonic qubits, which allow for bias-preserving C0 gates. So I'm at 4.5, I think. I don't know how much time I have. We started a little bit late, but I don't want to go over time. Can somebody tell me? Yeah, sounds good. Okay, right. So I can just wrap it up very fast. So it's important for you to not only have right type of noise, but it's also important for you to have the right code that can exploit that noise. And also you need to have the right way to implement the code in order to be able to exploit a leveraged noise for more effective error correction. We recently have a architecture for these atomic neutral atom qubits to implement the XZX code and exploit these biased erasures. I'm not going to go through the details. It turns I'll give you the highlight that the difficulty in doing so is that you, like I said, if you want to exploit biased erasures, remember biased erasures are like Z erasures on your qubit. You again need a bias preserving C0 gate, and there is no bias preserving C0 gate for neutral atom qubits. So then how can we use the XZX code properly to get effectively correct for bias erasures? It turns out that you could, for this specific kind of qubit, you can do something called as a measurement-based error correction and still exploit, still leverage, still preserve the bias that way, and use it for effective error correction. So let me actually skip all the details. It took longer than I expected. I'm going to just give you a highlight of the final results. Right. So let's just look at the figure over here on the top left. I'm plotting the threshold as a function of detected erasure fraction. Here I'm assuming a more complicated noise model where, or let's say a more realistic noise model where all my gates are going to be noisy. So errors just don't happen on the qubits themselves, but errors also happen during gates, and the measurements can be faulty. So this is what we call fault tolerance threshold. So this is the threshold as a function of the detected erasure fraction. And as the erasure fraction increases, the threshold increases. And in particular, for our predicted erasure fraction of 98%, the threshold can be as high as 10.3%. Now, in a similar noise model, if I just have poly errors, no erasure errors, then the threshold is about 1%. So you get an order of magnitude improvement in the threshold just because you went to the biased erasures. If I were to naively implement the XZX code the way people do it now, the threshold improvement would be smaller, about 8.2% versus threshold of 10%, which we see in this measurement-based error correction model. But you would say, who cares? Well, 8% versus 10%, it's a small difference. A small difference in threshold can make a large difference in the logical error rates. And moreover, it turns out because we can seriously reduce the overhead of the XGX code in the measurement-based model, because now I can use a switch, how do you call it? I can change the aspect ratio of my lattice to use fewer qubits and get the same amount of protection in my measurement-based model, but I could not have done that with the regular circuit-based model because I don't have bias-preserving CNOT gates there. But anyways, I'm going to just stop here. And just the main take-home message is that think about the details of the noise in your qubit. Don't just think about the fidelity, think about entropy of noise. And when you're thinking about making good error correcting codes, align the symmetries of the codes to the type of noise you're trying to correct. So I'll just stop here.